7, the chapter on physical and cognitive development in middle and late childhood. As you're reading this chapter, skim over the part on physical development. We're not going to spend very much time on that, although do focus on towards the end of the chapter. It talks about some of the educational issues, individualized education plans, IEPs, that you may have been familiar with or known people who had either if you've got a child or you've got a friend that might have had one in the K-12 system. The least restrictive environment, the idea that children should be put in the highest level of an environment that they're able to function in. Think back to Vygotsky's theory and the zone of proximal development. We want children to be challenged, but not overly challenged. So, we want to find that right place for them. And there's a lot of work that goes in, and a lot of research that goes into making those selections. The idea of inclusion is trying to include as many students in the regular classroom as possible so that they can have the full experience of the world that they're learning to live in. When you think about cognitive development now, what develops, right? So they learn to classify things into categories. They learn to put things in order. We call that seriation, from largest to smallest, for example. Transitive inference, I'll talk about in just a second. Cause and effect. They start to understand that a pencil doesn't just fall on the floor, but something knocked it and it rolled and then it fell on the floor. So they understand the intervening steps there where they hadn't when they were younger. Spatial thinking, I've got some slides I want to show you on spatial thinking and how they draw, because it's very interesting. If you're around children at this age and you can see their drawings, ask them about them. And just sort of ask them, what the drawing is about, and can you tell me more about that without focusing in on anything specific. If it's a child that's important to you, write it down on the back. You think you'll remember later, but most of us don't, because there are a lot of things that happen, but it can be really interesting to go back over later to sort of see what those developmental progressions were. Conservation, this week you'll be working on an assignment where I'm asking you to engage in a task that is as difficult for college students as the water pouring conservation is for small children. And so it's not meant to show you that some people are smart and perhaps, if you struggle with it, maybe not. What it means is you are smart. What it means is it's hard work. And so I hope that you think about that, and also try it out with other people if you can, because it can be a hard thing to understand the first time you do it. Once you've seen the solution for it, try it with others and see if you can explain it to them. Being able to teach it to somebody else is a good measurement of how well you've understood something. And then inductive and deductive reasoning, whether we take evidence and come to a conclusion, or whether we start with a conclusion and then try and find evidence that supports that. Okay, so transitivity. A is longer than B, C is shorter than B. Is A longer or shorter than C? So students or children start to understand that even if you haven't measured the relationship between A and C, you can answer that question because you know other information. So their thinking is becoming more complicated, more nuanced, and they're starting to be able to draw those kinds of connections. Spatial thinking, this slide shows a progression of successively older children drawing liquid in a tilted jar on a table and people or trees on a hillside. So when you look at the first one, there are people, there's a jar, but the jar is not tilted, the people are not on the hillside. And as children get older, they start to see, okay, the jar tilts, but that's not exactly how liquid works in a tilted jar. In the third one, they're getting closer. And then in the last one, the jar is tilted, but the water level stays even with the horizon, and that's how water would work, or liquid would work. The same thing with the people or trees on the hill. Initially, there's a house and a tree on the hill, but they are perpendicular to the landscape and not to the horizon. And it isn't until they get older that they understand those kinds of relationships. Pre-operational children, this is a picture of a bird, and when you think about how that differs from an older child, look at the placement of the eyes, look at the placement of the wings, look at the size of the legs relative to the size of the body of the bird, and think about whether that bird would be able to stand up. So that's a very young child, but slightly older children might be able to draw something like this. And so here you've got clearly dogs playing soccer. And if you ask, and they did ask the child why they drew it the way they drew it, the two dogs on the one side each have four legs. and they're playing soccer, they're facing in different directions, but they asked, why does the other one not have four legs? And what the child said was, well, it does have four legs, but it's standing still, and so you can't see the ones on the other side, where the two dogs that are together are running, and so you can see all four of their legs. So a huge cognitive advance in how they're thinking about spatial operations and how they're thinking about their own drawing. So in the next series of slides, and you could pause on this slide if you want to and try it, that's what I do in a seated class. Draw a picture of a mother and a father holding hands in a park with their baby on the grass in front of them and a tree far off behind. So pause the video, do your own drawing, a small sketch, nobody else will see it. Okay, did you pause? So here's what a 4-year-old did with that prompt. And there aren't trees, and you can't tell if they're in a park. And this is what I call paperclip people. Very often, very young children will draw paperclip people or tube people, where there are just two lines coming down from a head. And when you think about it, think about what is salient to the child, what's relevant to the child when they look at another person. It's definitely their face first. And so they're spending a lot of time and attention on the face of the individuals, but not on the other parts of the prompt, which actually they may have forgotten once they started drawing. A 6-year-old, however, has more information here. So there's definitely something above and something below, but everything is right on the horizon, right? You don't see things that are clearly behind other things. So mother and father, baby, tree, everything is in the same line. With an 8-year-old, there's definitely things in the foreground, middle ground, and background. And there's more attention to the prompt, right? There's a baby on the ground, they're holding hands. So they're getting more information into their drawing and thinking about it in a different way. And then a 10-year-old, very different. You've got a swing, there's a rainbow, there are all kinds of creative embellishments. But each of these things, it isn't just pointing out whether the child is getting better at drawing, but how they're approaching it. And that's a sign of how they're thinking. And that's what Piaget was interested in. How are children thinking, and how is their thinking different at these different ages? So moving on to other aspects of thinking, if you've had a child in elementary school in the last 5 or 10 years, you may be familiar with number bonds. If you haven't, and you didn't experience this, teaching math evolves. And one of the ways that it has evolved recently is using number bonds rather than 20 or 30 or 40 years ago, you might have just memorized multiplication tables. Now you start looking at how to combine two numbers to make a third, how if you have the sum and one of the numbers, you can deduce the other one. And so they have number bond worksheets that get progressively more complicated as the child gets older. I don't know that they start in kindergarten, but probably in first grade, they'll start with these worksheets in the current K-12 system. And who knows, like by the time I'm retired, they may have a different way of teaching math because there's research on teaching math and what's working. And what they want to do is build these long-term skills that will allow them to do more rather than rely on their memorization. So from Piaget's perspective, all of these cognitive advances don't occur at once, right? So sometimes you get linguistic advances, sometimes you get number advances, sometimes you get spatial awareness, but they're not all on the same continuum. They're developing at different times. But by the end of this stage, they will have mastered all of these things. And so it's sort of at the beginning they don't have it, at the end they do have it, and it comes in, at different ages or different times. When the chapter turns to memory, talking about children's memory, if you've known somebody who was diagnosed or tested for ADD or ADHD, sometimes they will use memory span or working memory span tests. And one of the ways they do that is using digit span tasks. So when you're testing for ADD and ADHD, some of what you're testing for is their ability to remain concentrated when there's a shiny thing, but also to remain concentrated when something is really boring and to persist at that task. So digit span tasks ask you to remember numbers. I'll switch to one. So you would read out to the child 6, 9, and then pause, and then the child would write it down. It's important if you're actually doing this to have a cadence where you don't do it really quickly. Like if I say 4, 1, 7, 9, you can remember that really quickly. But if I say 4, 1, 7, 9, and then I pause and then say write it down, you have a chance for things to leak out of working memory. And so that test of working memory is how much can you hold in working memory over a period of time. So when I'm doing it in a classroom, I actually count to 5 in my head in between each of these numbers. You also use a backward digit span task where you might say 9, 7, 5, 9, 2, 6, 1, and then pause and then ask them to write it the other way, and to write it continuously, not to start at the back and write it that way. And so they would have to write 1, 6, 2, 9, 5, 7, 9 in that order. So again, the longer, and then you figure out where they fail, and where they're not able to do it. And as they can consistently not be able to do it with those number of digits, then that is their digit span for that. That is their working memory capacity. And you can compare it to the working memory capacity of other individuals who are in that same age range or that same cognitive stage. When it comes to thinking, convergent and divergent thinking, convergent thinking, you converge on one answer, and divergent thinking, you ask them to, so to speak, brainstorm and think of as many uses for a paperclip as they can. You've probably been in some sort of a session where they asked you to do that. If not, good luck to you. Those are not my favorite sessions. They also start to talk about or think about how they're thinking, and we call that metacognition. They're aware of their own thinking processes. A 3 or 4-year-old is not aware of that. A 7 or 8-year-old is aware of how they think and how they learn. The same thing with memory. They start to understand how they remember things, and there are strategies to remember things. And then brainstorming, when you think of divergent thinking, one of the exercises that I often use in a seated class is think of all of the people that you can think of who have ever existed, who are the most intelligent people ever. And we sort of brainstorm, but I ask people to write it down first, because if you write down your brainstorming responses first and then share them with others, you get a really wide range of answers. If people are saying them out loud, as soon as somebody says Marie Curie or Einstein or somebody else, then a lot of people, or Plato, people will go down that pathway and think of other ones that are similar to that, which is also part of brainstorming. But the way that you get the most diverse set of information to begin with is to ask everybody to do it silently first. So I don't know who you think the most intelligent people are ever, but I would encourage you, before you go on in this video, to jot down your top 10. Like, who are the top 10 people who just pop into your mind when you think of the smartest people ever, living, not living? You could know them, you could not know them. Who are they? Okay. Using strategies. So helping kids at this age use strategies, and it works for kids. It also works for adults. If it's material that they are struggling with, encourage them to overlearn it. Once they think they know it, keep studying it, keep studying it, keep studying it. Because once it truly becomes something that is ingrained in you, it becomes more automatic, and you can add more things to it. That's how neural networks work. Then once you've got a schema in your head, learning one more thing about that thing can be quite simple compared to when you learned it the first time. Using visual images. So if they're doing note-taking, drawing pictures, if they're trying to learn something, trying to draw an image of it, it doesn't matter whether it's good art. What it matters is that they are using the cognitive process of trying to diagram something in some way. Being an active reader, sort of thinking about how what they are reading applies to themselves. So if they're reading a story about a family, if they're reading a story about nature, how does that relate to the experiences that they've had, things that they already know? In math problems, writing down the steps. Your teacher always tells you to show your work, which can be annoying, especially if you don't really understand the work that you're doing. But writing down the steps can help them to understand, if they get the answer wrong, at what point did it go wrong. And so you don't have to study the whole process again. What you need to study is the part that you got wrong, and then forward from that, and not all of it. So that can be helpful. Retrieval practice, practicing to quiz themselves, to try and think of something, to write things down. All of those things are a cognitive process that strengthens the neural network in your head, and helps you to be able to use that information and to have that information come into working memory more fluidly when you need it in the future. And then developing cues. If you need to remember a set of information, what are the ways that you can do that? Can you use an acronym? Can you use a song? Can you connect them together in a story in some way? What are the cues that you could use to improve your memory and improve your ability to bring things into working memory and work on them.